Welcome back. Okay, so now we will learn how to actually compute the Euclidean commute time distance. So we will go over the closed form solution, and then we will also go over an iterative algorithm to computing it. So for the closed form solution, we need a few definitions. Okay, the first one is the adjacency matrix. Adjacency matrix A. Okay, this is going to be a matrix of constants aij, where aij will be equal to the weight of ij if ij is connected, ij connected, and it's a unit equal to 0 if ij is not connected, okay, otherwise. So you can immediately see that if your graph is not very connected, then the adjacency matrix is going to be sparse. Okay? And the second thing is the diagonal matrix D. So D is just some diagonal matrix. I'm gonna write. It's going to be the row sum of A. Okay, AI dot. Okay, where AI dot, that's going to be equal to the sum of the row I over every single entry, okay, of every single j. So the reason why we define D is because we need it in the definition of Laplacian. The Laplacian L is equal to D minus A. Okay, this Laplacian is going to be very important, so I'm going to highlight it. So before I actually talk anything about the Laplacian, we need to know that the Laplacian L is not full rank, okay? Okay, why is that? Because L of 1 is just, this is just a vector of 1s, okay, is equal to D minus A times 1, right? And so, well, let me just write out everything, okay? What is D? D is equal to the sum of the first row of I, right, over a single row, and then the second row of the second row of A, and then every single thing, all the way down to the last guy, the nth row of that's what D is. These guys are zeros, and then minus, what is A? A is just A11, A12, right, blah blah blah, A1n, A22, ANN, right? So if you take this guy, you multiply by 1, a vector of 1s, so we'll just write it out, right? A vector of 1s. What is that equal to? So we will distribute the 1 and multiply these by these two matrices 1 by 1. So if you take this first vector and then just multiply it to the matrix, you will what would this matrix be, right? So it would just be A1j, and the second one will be the sum of A2j, right? So all the way to A and j, where these guys sum over j. So it will be this guy minus what is A times this guy. So I hope you see it already. Is I, A, J, J, blah 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 blah, A, N, J. Okay, so this is equal to 0. Okay, so in other words, the vector 1 is in the null space of L, right? So basically the null is not equal to empty, and so by rank nullity, L is not full rank. Okay, so that's cool. And the reason why we want to show L is not full rank is because if you want to invert L, then you can't do it, right? But in life, we know that if there's something that you really want to do, you can still do it if you really want to do it, right? And that's also true in math. So we have the pseudo inverse of L. And this is, I don't know if people in our class have seen this, but the more Penrose pseudo inverse is just a way to sort of invert a matrices, right? Invert in quotations, so that if your matrix is not full rank or if it's not square, you can sort of still invert it, and it satisfies a bunch of different properties, right? So it's equal to L plus like this, and then there's a bunch of properties, and that's not the point of this class, right? I will just use this matrix as if we know what it is, right? It's just some matrix. It's also unique. The more Penrose inverse is unique, right? But just any general pseudo inverse is not, but the more Penrose one is. So given that we know what this is, we can compute the average commute time. Compute n comma ij via. Well, okay. Remember, this thing is the average number of steps required to go from I to j, then from j to I. Okay. And this guy, you can show that this is equal to the volume of the graph. So this is just the sum of aij over all I over all j. Okay. Volume of the graph times the ei minus ej transpose, where ei is just equal to a vector of zeros except that position 1. Okay, this is I, except position I is equal to 1, and then it's just 0. So these are just basis vectors. 0, 1, this is our position j, and then 0, 0, 0, 0. This guy is equal to this times the pseudo inverse, the more Penrose pseudo inverse of the Laplacian. Let me remind you what Laplacian is. Laplacian is defined up here, and then we times the right vector of this difference, right? So you have like this weird quadratic form times the volume of the graph. So this guy is the closed form solution for how we compute the Euclidean commute time distance. Okay, and for a proof of this, we are going to just leave it, and this is basically an appendix of this paper that I cited in my reference. You can look at it on GitHub, but there's a few observations that we need to make. Okay, let me go up to the. Let me just erase everything. Okay, so first of all, observations. One, L plus is symmetric. Why is this? Because L is equal to D minus A, right? D is a diagonal matrix, so that's symmetric by default. A is also symmetric because we have defined weight to be symmetric. Right? So the difference of two symmetric matrices is still symmetric. And just by properties of pseudo inverses, L is symmetric implies its pseudo inverse is, right? And the way that I can remember these properties is that basically whatever property L has, the pseudo inverse has it too. So if it's invertible, I mean if it's okay, well, I don't know if I should say this, but this is kind of true in general. Okay, if L has some property, the pseudo inverse usually has that property. Okay, you can prove this, but it's not the point. So the second property is that L plus is positive semi-definite. Okay, PSD. So if you don't remember what that means, it's just if you right and left multiply it by some vector, this guy is going to be greater than or equal to 0. Okay, or another way of saying it is that the eigenvalues of the eigen evals of this guy is all greater than or equal to 0. Okay, it's just some definition. So why is this true? We know this is true because we know that L is equal to D minus A, right? And where D I this is equal to the sum of A I J over all J, right? And what is A? So A is equal to, let's say if we look at the ith row, right, then this is equal to the AI1, comma AI2, blah 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 AIN. And so if you take the diagonal of how should I say this? So basically L is diagonally dominant. I mean, I hope, how do I write this? I hope this is obvious, right? So if you take this diagonal over here, and then you subtract every term off of here on this guy, this term is greater than all of these terms combined, okay, and that's what diagonally dominant means. And this term is greater than all of these terms combined, and this is just true, right? Because D is all the sum of all of these guys together, and if you take away one term and then you just look at everything else, it's going to be smaller, okay. So L is diagonally dominant, and by that implies L is positive semi-definite, okay. And if L is positive semi-definite, then the pseudo inverse is, right, by my proposition. So proposition that L property implies L pseudo inverse property. Okay, I don't know if this is true in general. I mean, it's probably not, but I think a lot of the property it has, this is generally true. Okay, so why did I say all of this stuff? And it's just because we want to establish that L plus the pseudo inverse of L will define an inner product. Between vectors. Okay, so what does that mean? If you have two vectors, if you want an inner product L, this you can define it as essentially x prime L plus y. So in some sense you can measure the distance between two vectors using a positive semi-definite matrix, right? And what this means is that if you want to measure the norm of a vector using this matrix, you can do that, right? It's equal to L x times plus x. Well, there's a transpose here. And then you take the square root. So this is just norm, right? If you have a square there, then you have a square there. But in general, whoops, that's a okay. So because there's this square root, right? This is essentially why the Euclidean commute time distance is defined as a square root, right? This is the Euclidean commute time distance. This is where the square root comes from. And so for the students in Biomath 203, right, I ask you to show that L plus is, in general, I'm not super sure exactly how usually you compute L plus. Computing L plus. Okay. So if you just have some general pseudo inverse, some general matrix, you want to compute the pseudo inverse, I'm not sure how to do it. I think there's probably some library, right? Julia definitely has it. It's just called the pinv. But according to our setup, right, we can actually compute it by doing this guy. Minus 1 times 1 transpose divided by n. This guy inverse minus 1. Remember 1 here is a vector of 1s, okay? This guy is just a 1, 1, 1, 1, 1, right? 1, 1 transpose divided by n. So 1, 1 transpose is just equal to a matrix of 1s, okay? Everywhere is just 1, 1 everywhere. So this is a claim in one of the papers that I cited, but it's never really proven. So we will leave this as homework. Okay, this is homework. And also in computation, right? Remember that when we want to solve things like ax is equal to b, right? If you want to solve for x, we don't never do. Let me just write it out because it's important, right? X is equal to a inverse times b, right? Right, you can write this using math, right? But in practice, you actually never have to compute this guy. Usually you do it using some factorization, right? So for instance, the people who proposed this algorithm, this method in the first place, proposes to do Cholesky. Okay, so Cholesky means that you can factor some matrix A as L times L. Well, okay, L is not a. I don't know if I should use L. Well, okay, I should just you can factor the matrix into a lower triangular matrix times the transpose of the lower triangular matrix. Okay, this L is not equal to this L. Okay, this is just a general factorization. So if you are able to do this factorization, right, then ax is equal to b can be solved using LL transpose x is equal to b, right? Just substituting a and l. Then this is if and only if L transpose x is equal to some other vector, you call it y, and L times y, so now this thing is y now, is equal to b, right? So basically you want to solve this equation and this equation once you have the Cholesky. Compute this. And why is this easy to solve, right? L is a lower triangular matrix. So you have a matrix that looks like this, right? And then this is 0 here times some vector y, well, let's call it y1 yn, right? And this is equal to b1 all the way to bn. So this first row, right, it's very easy to solve for whatever this guy is, right? So you can do that. And then in the second row, because you know what this guy is, you can also solve for what this guy is, and you use on the second row. So you can see that you can just do this row by row, and it would be much easier to solve than just inverting a matrix. Okay, so what have we done? This is the closed form solution for computing the Euclidean commute time distance here. And if you have a matrix that's like super big and you can't really do this, one thing that you can do is to use simulations, right? You just do Markov chain Monte Carlo, so you have some graph, and then you just do a bunch of simulations for like, you know, a million times or something, and then eventually using your simulations you can get the answer. And in fact, this is one of the strategies that the original authors proposed. But in the next video, we will actually tell you how to do iterative methods. So that iterative methods is going to be, at least in my simulations, much faster than computing all of these stuff. Okay.